Hello, Mr. Betts here. Let's take a look at a couple examples where we have to take higher order derivatives, but they're a little bit more complicated. This first example, it falls into level two because it's mixing a graphical and an analytical definition of a function. Let's kind of dive into it here. Lots of information given in the problem here, and I tend to like to jump to what the question is first, and then we'll use the information in the problem as needed. Ultimately, what we want to find is the derivative of h, the second derivative of h, evaluated at 2. And so to do that, we're going to need to know what h is, and that's given to us right here. So I'm going to start by just taking the derivative of h in the form that's given to us, and then the second derivative, so the derivative of the derivative, and then hopefully we'll have enough information given to us in the problem to be able to fill in any blanks that we have. So starting by taking the derivative, h prime of x is going to equal, so we have x squared times f of x. That's going to be a product rule problem. So we're going to have derivative of the first is 2x times the second plus the first times the derivative of the second. So there's our first derivative of h. In order to find the second derivative evaluated at 2, we're going to have to take the derivative again. So let's take the derivative of that. Looks to me like we're going to have to use a product rule twice. So derivative of the first in that first term is going to be 2 times the second plus the first times the derivative of the second. And then for the second term, we're going to have derivative of the first times the second plus the first times the derivative of the second. So just starting out this problem, the only thing I really used so far is this definition of h right here. Now the question's asking for the second derivative evaluated at 2, so I'm going to plug 2 in for x. So we're going to have 2f of 2 plus 4f prime of 2 plus 4f prime of 2. I could probably combine those two terms if I wanted to get 8f prime of 2 plus 4f double prime of 2. Okay, so now I need to take information from the problem and plug it in for all this f stuff here. So first of all, in the problem, we are told that f of 2 is negative 3. So where that f of 2 is here, we're going to put negative 3. So this is going to equal 2 times negative 3 plus 8 times f prime of 2. So if we look at the graph here, and we need to be really careful about this, we're told that this is the graph of f prime of x. So in red, this graph here is the derivative of f. It is not f, and we need to be really careful to not use that as f. So if we want to know what f prime of 2 is, then we're looking at the graph of f prime at x equals 2. It's just the value of this, which is going to be 4. So f prime of 2 is equal to 4. So this is going to be 4 here, plus 4f double prime of 2. So this is the second derivative of f at 2. So this is where the tangent line in this picture comes into play. This is the first time we've seen this idea, but since in red we have the graph of f prime, then the slope of a tangent line is actually going to be given by f double prime. So the derivative of the derivative is the second derivative. So the slope of this line right here, which is, we can just see using the lattice points, the slope is 1/2. That's going to be the second derivative of f evaluated at 2. All right, so again, since the graph of the red is f prime, the slope of the tangent line of f prime is going to be given by the derivative of that, which is f double prime. So that's going to be 1/2. And if this were a free response question, we could just box that and be done. We can go ahead and simplify, though, to get a numeric answer. So we're going to have negative 6 plus 32 plus 2. So that's going to be 34 minus 6, which is 28. In the second example here, we've got an implicitly defined relation, and we want to take the second derivative. So we're going to start the same way we do any other problem. If we need a second derivative, we're going to start with the first derivative. Since it's implicitly defined, I'm going to use implicit differentiation and take the derivative with respect to x. So taking the derivative of each term with respect to x, I get 2x plus 2y dy dx, since the y is an inner function in terms of x. So I'm using the chain rule there, equals 0. Solving for dy dx, I get, subtracting the 2x over and dividing by 2y, canceling 2's, we get negative x over y. I could have left the 2's in there and it would have been perfectly fine. Thinking ahead, though, if I want to take the derivative, I want the first derivative as simple as I can before I take the derivative of that to go on the next step. So now, since I want the second derivative, I'm going to take the derivative of that with respect to x. So on the left side, the second derivative of y with respect to x is going to be written like that. On the right side, I'm going to have to use the quotient rule. So low d high, so y times negative 1. So that's the derivative of negative x with respect to x is just negative 1. No worries about implicit differentiation yet. Minus high d low. So the derivative of y is going to be 1 times dy dx because of implicit differentiation and using the chain rule, and then all over the square of the bottom. So let me clean this up a little bit here. We're going to have negative y plus x times dy dx all over y squared. Now, this is the second derivative with respect to x, but it's not an okay answer because we have that first derivative involved in our answer, and we know what the first derivative is, so we can replace it. So this is going to equal opposite of y plus x times negative x over y all over y squared. Again, if this is free response, box it, you're done. I like to simplify answers like this because it's good practice in case it's a multiple choice question and we have to match an answer. This is a complex fraction, and to get rid of complex fractions, we can multiply by a common denominator. So I'm going to multiply top and bottom by y, and I'm going to go ahead to the next line here. So we're going to have the opposite of y squared. The y's in the second term are going to cancel, so it's just minus x squared all over y cubed. Now that's a simpler answer, more likely to be a response for multiple choice. I do want to point out that we can do something kind of interesting with this one. So before I move on, I'm going to say this is good enough here. In fact, remember, this was good enough here even. However, this is an interesting one where we can actually use the definition of the relation itself to simplify even more. So it's not something that's immediately obvious, but looking at the numerator, if we factor out a negative 1, that leaves y squared plus x squared. And in the problem, y squared plus x squared is 25. So we can replace that y squared plus x squared in our answer with 25. And so this is going to be the same thing as negative 25 over y cubed. So this is actually the simplest way we could write this answer. It's not an answer that I would expect you to get to if you were doing this on a free response question. It is possible on a multiple choice question that this is the answer that they're going to be looking for, but not really likely. I will say that if we want to take another derivative, it's going to be a lot easier to do with this form than it is with this one. So being able to do manipulations like this can be helpful if we want to make things as easy as possible on ourselves.